So next speaker is Fabio Di Cosmo, and he'll talk about emergent type 2 and 3 factors in Schwinger picture of quantum mechanics.
Okay, so first of all, thank you very much for the invitation. It's a real pleasure to talk here in this occasion, at the occasion. Actually, I met Bal in 2017 in the occasion of his birthday. It was in Zaragoza, and I met for the first time him, and I was really impressed by his curiosity and the amount of questions he was always asking to everybody. And actually, I hope today to give an answer to some of his questions. And this is why I've chosen this type of this talk to talk about the emergent type 2-1 and 3 lambda factor, which is actually connecting with the question which he was asking right before to Alberto. This work, we are actually the notion of this type 2-1 and 3 lambda factors using groupoid algebra is not a novelty. There are actual papers works by Takesaki and by also a lot of von Neumann itself, where these factors are obtained using the notion of groupoid algebra. What we are trying to do is to reinterpret them using this Schwinger picture of quantum mechanics. This work is in collaboration with Alberto, Florio, Peppe, and also with Arturo Condera, a student from Bari who was visiting us last semester, and Paolo Facchi. So let us just will talk about the plan of the talk. So first of all, a short summary of the groupoid approach to quantum mechanics, which has already been extensively explained by Alberto and Beppe in their talks. Then I will focus on this system, which I will call in the rest of the talk the infinite qubit chain groupoid, which should be the groupoid corresponding to the infinite direct tensor product of algebras in this sense, the one that are associated to powers factor, to hyperfinite factors. I will introduce a proper system of our measures on this groupoid, and then I will construct the associated groupoid algebras. I will talk about the Mita-Takesaki modular theory for these groupoid algebras, and then I will generalize slightly this model in order to describe a sort of Ising model. Okay, so just recalling the main ingredient of this description, we associate to every physical system a measure groupoid. In this case, we have the groupoid is a set of transition with two maps. Omega is the space of objects, and G the space of transition. We have two maps, source and target. There is a partial composition law among transition, which is associative. There are units and there are inverses. The groupoid of pairs over 2 points is what we have associated with the groupoid which we have associated to the qubit, and what we have is actually 2 units. Then there are the transition alpha and its inverse. The algebra of observables is obtained as the reducible Neumann groupoid algebra. I will later explain how to construct this groupoid algebra with more details. So for the moment, I will just show the one example. This algebra is constructed out of the functions on the groupoids, complex valued function. And for the case of the qubit, or the groupoid associated with the qubit, what we obtain is actually that the function can be arranged to form 2x2 matrices. And there is this space of function can be endowed with a convolution product. And so we obtain a groupoid algebra, which is isomorphic to the algebra of 2x2 matrices. It can be generalized to the groupoid of pairs over n objects, obtaining in this case the space of matrices n times n matrices. Physical states, in this talk I will consider them as positive linear normalized functional on the groupoid algebra, so that we have the usual interpretation of the evaluation of a state on an element of the algebra as an expectation value. But of course, as was proposed by Alberto, was told previously by Alberto, we can use a different interpretation using positive definite function on groupoids and associate this with the probability amplitudes. About the evolution, In this talk, I will consider automorphism of the groupoid algebra, but again, one of the main contributions, one of the most interesting contributions given by Schwinger is exactly the dynamics can be obtained via a quantum action principle, as was already explained previously by Alberto. And then for a composition, we studied up to now two types of composition. One is the direct composition corresponding more or less to the tensor product of algebras, and one is the free composition, which instead we have shown in some example it's connected with the free product of algebras with amalgamation over a subalgebra. Okay, so what is the system that we want to describe? Well, in order to, we have seen that the qubit was given by this type of groupoid here, two objects. So the first idea was to consider an infinite product of this type of groupoids, but this obtaining this way the space of object, which is the space of sequences of all 0 and 1s, and then two copies of this space. This type of groupoids, the groupoid of pairs over this space of object, is not good candidate for obtaining this type of the factors which are of type 2(1) or type 3 lambda, because what we obtain in this case for a groupoid algebra is just a type 1 factor, which is all the bounded operator on the Hilbert space on this space of omega infinity. So we have changed this approach, and we have considered a subset of omega infinity gamma, which is the space of all sequences which are definitely 0. So there is an M after which all the X are 0. Since the set 0, 1 is an abelian group under addition modulo 2, we can extend this operation component-wise, and we obtain a group omega infinity and gamma are both group. Gamma in particular is a subgroup of omega infinity, which is a countable and abelian subgroup. Since it is a subgroup, it can act, of course, on omega infinity, and out of this action, we can construct an action groupoid, which as already was explained previously by Alberto. In this case, these are simply I changed slightly the notation because I've used X here as the target. So it's already the result of the application of X0 to X plus X0. But again, the units are simply connected with the unit of the group and the object X. And the inverse contains the inverse of the transition, which in this case of the element of the group X0, which in this case coincides with X0, acting, and the target is replaced by the source. Okay, so what is now the main ingredient to construct the groupoid algebra? Well, what we need is a left invariant. For group, what we need is an R measure in order to construct this convolution product. Since what is already told by Alberto is that a group is a special case of a groupoid where the space of object is made by only the one unit. There is only one unit. In this case, what we have is that there is only a R measure. In the group case, so what we are obtaining, we generalize this R measure to a R system of measure, a left invariant R system of measure. So as a system of measures supported on the fibers of the target map. How do we construct this measure in this case? Well, we start from a measure on omega infinity, because we have the groupoid is simply the product of the group gamma with omega infinity. Therefore, on omega infinity, we consider the following measure structure. Omega infinity can be seen indeed as a infinite direct product of measure space. On each of these omega 2, we consider a measure which is an atomic measure, probability actually, which has value lambda on that the 0 and 1 minus lambda at 0.1. Then we can take simply the infinite product of this measure, and this is a measure on the sigma algebra generated by the cylinders. What are the cylinders? Well, if we take, for instance, n equal to 2, what we are doing actually is to consider a partition of the interval, this space omega infinity of all sequences between 0 and 1 is actually a subset, can be mapped into the interval 0, 1. They are actually the dyadic numbers, they are called, because we can consider this as a an expansion in the two bases of every decimal number. And then what we are doing in a cylinder instead is to consider a partition of this interval into subinterval, and the cylinder is just generated by one of the subset is just one of these. For instance, when n is equal to 2, we have that once the cylinder generated by 0, 1 is just this subset, and so on. What I will consider is lambda between 0 and 1 half. The case 0 is excluded because in this case we have a degenerate situation where the algebra is abelian, and I will not consider it. Okay, now what is the measure on the full groupoid? It's simply the product of the counting measure on the group, which is an abelian uncountable group, times the measure on the base space, on the space of object. As we can disintegrate this measure with respect to the measure on the base space, on the space of object, using a system of measure mu of x, which is written as follows, as the delta measure at the point x times the counting measure on the fiber. And this measure has a support exactly only on the fiber of the target map. What are the properties of this system of measure? Well, they are left invariant in the sense that if we act with the groupoid, with a transition of the groupoid, we are mapping the fiber over the source of alpha to the fiber over the target of alpha. And the measure is mapped, the measure on the source on this fiber G of S of alpha is mapped into the measure into the fiber on G of T of alpha. Another property that satisfies this measure is that when we consider the inverse map, the push forward of the measure with respect to the inverse map is absolutely continuous with respect to the measure mu. And this, the Radon-Dinotin derivative is the modular function. It's called the modular function. In particular, for the groupoid, this is a groupoid homomorphism of the groupoid G into R plus. And for the groupoid which we are considering, which is which depends on the choice, for which we have the choice of measure with lambda, characterized by lambda, what we have is that this groupoid homomorphism is just a power of lambda, of the factor lambda over 1 minus lambda, or the quotient lambda over 1 minus lambda. Okay, so we have now introduced this system of measure. How can we construct a groupoid algebra? Well, first of all, we consider a subset, a subspace of function of integrable function for which this new measure fi is smaller than infinity. This measurement actually consists basically in the integration of the function and the adjoint of the function with respect to the fibers. And this way, when we integrate with respect to the fibers, we obtain a new function only on the object, and we are taking the L infinity norm of this new function on the space of object, and we are taking the max between these two objects. What we obtain is that this space I of G is a Banach star algebra under the convolution product, which for this special case is reduced to a sum, but in general will involve an integration over the fibers at each point, over the target of each transition. The involution instead is written in terms of the inverse map, the complex conjugation, and the multiplication by the modular function. So now we consider, so up to now we have only a Banach star algebra. In order to obtain a von Neumann algebra, we need an inverse space on which this function should act as bounded operator. To do this, what we can do is to consider a subspace of the intersection of this space I of G with the space of square integral function, such that also f daga is square integrable if f is square integrable. What we can claim is that this space A is a left Hilbert algebra, where the scalar product of the Hilbert product is simply the product of square of L2, and the elements of the algebra A F act on themselves by convolution on the left. This is why we call the choice of this action, this left action, is what gives rise to the reduced von Neumann groupoid algebra when we take the B commutant of this representation. On this groupoid algebra, which this for the case that we are considering depends on the parameter, on the choice of this parameter lambda, so on the choice of the measure, there is a canonical normal weight, as it is, which is the one characterizing the scalar product of the left Hilbert algebra. When we use the measure mu, this canonical weight is expressed in terms of the integration over the space of object of the restriction of the function in A. Okay, so now what we want to show is that these groupoid algebra are actually factors and non-isomorphic factor depending on the parameter lambda. To do this, I will introduce a different algebra, a different type of family of algebras, which were introduced by Vukansky in 1956, just to present some example of non-isomorphic von Neumann factors of type 3. What he was using was actually the group measure construction, which was firstly employed by von Neumann, using as a group the countable group gamma, acting as exactly on the space omega infinity endowed with this infinite product of measures. The factor that he was considering, that I will call P lambda of G, was generated by the unitary representation V of psi of y0, which is written here in terms of this delta function, and by the algebra of multiplication operator by function phi on L infinity. When lambda is equal to 1/2, this is the hyperfinite type 2-1 factor, and this was proved already by von Neumann himself. Whereas for lambda between 0 and 1/2, what we obtain are non-isomorphic type 3 factors, because the action of gamma on omega infinity is free, ergodic, and non-measurable. This non-measurability property is what actually characterizes the type 3 factors, because it means that there are no semi-finite traces. There are not finite traces. What is the claim here is that mu lambda of G is isomorphic to this P lambda of G for every lambda. And to prove this, what we want to show is that any operator into lambda of G can be expressed as an operator in P lambda of G and vice versa. When we do this vice versa, we see that in the new lambda of G, there is always an abelian subalgebra corresponding to the function f on the space of objects, which acts as a multiplication operators. So they form an abelian subalgebra. In this particular case, we have also a unitary representation of the group. And this unitary representation of the group can be interpreted in this groupoid language as a characteristic function on a bisection of the groupoid. We have already used in another paper that this bisection can have an application in the tomographic picture in order to have a tomographic reconstruction of state. So we could try to extend this construction also to this algebra which are infinite. Okay, let us now introduce some notion of Tomita-Takesaki modular theory. So first of all, let us come back to the left Hilbert algebra A. And on this left Hilbert algebra, there is an operator S, which maps A into itself, and which maps every function f to its adjoint. This is actually an unbounded operator on the Hilbert space, which is the completion of A, which is densely defined on A, and which is closable on this, which is also a closable operator. Therefore, there is a polar decomposition in terms of an operator J and an operator delta. This operator J is an anti-unitary operator, which for this for the groupoid algebra is a very simple expression, which is just the multiplication by the modular function times the adjoint. What we have is that the conjugation by this anti-unitary operator gives rise to the maps the von Neumann groupoid algebra to its commutant. For this left-Hilbert algebra, the commutant is just the convolution from the right. Then the modular operator delta is a positive operator, and in this case, it's just a multiplication operator. So we have a very simple expression for this modular operator and for the associated modular automorphism, which is given by the conjugation by the unitary operator delta to the minus IT. Since it is a multiplication operator, we can also immediately write the modular Hamiltonian as the logarithm of this delta function. And what we obtain is that the spectrum of this Hamiltonian is just characterized by this parameter logarithm of 1 minus lambda over lambda times k alpha. And this is in agreement with the Con's classification for the hyperfactors of type 3 lambda. Moreover, the canonical weight that I've introduced previously satisfies the Km's condition with respect to this modular automorphism. And in particular, for the groupoid algebra that we are considering, since delta is a groupoid homomorphism, the modular automorphism maps pi of f to the representation of the function f times the delta to the IT. So it's a very simple expression for this modular automorphism. Okay, so let us briefly recall what I've told up to now. So using another measure, we have introduced a groupoid algebra. We have found that there is a modular function, which is this groupoid homomorphism, delta to the minus 1, which generates the modular automorphism. And using this R measure, we have also constructed a canonical weight, which is a Km's weight with respect to this modular automorphism. So what we can pose as a question now, we can ask as a question now is, if we consider a different homomorphism, can we find another R measure mu tilde for which we have a new groupoid algebra, a new KMS weight satisfying, which is KMS, it satisfies the KMS property with respect to the associated modular automorphism generated by this new modular function? Well, the answer is in the affirmative, but to show this, one has to introduce, as was done by Alberto, the notion of Con's transverse function and transverse measure. I will not enter into this now. What I will try to do in the rest of the in the time that is left is to provide an example of this construction. But before doing this, let us show what are all the possible homomorphism, groupoid homomorphism from G to R plus. Since these are delta function are positive, they can always be written as the exponential of a function S, and this function satisfies a logarithm property with respect to the composition, and these are exactly the condition we introduced previously by Alberto, defining a DFS function, a Dirac-Feynman-Schwinger function, and actually defining providing a connection with the Lagrangian. So using this construction, we are interpreting now this DFS function in a different way, connecting them to the Tomita-Takesaki theory of the group of a groupoid algebra. So when we consider the groupoid gamma, the action groupoid of gamma on the space omega infinity, we can find a homological characterization of all these function S, because we can consider the function on this groupoid as the tensor product of the function on gamma with values in the function of omega infinity, and this space of function on omega infinity is a gamma module with respect to the action by the group, which is the left action on the space of function. Therefore, there is a natural homology on the space on on the function, the end product of the group with values in this G module, in this gamma module. And in particular, when we consider the one cochain, the differential operator on this one cochain provides exactly we can reinterpret using this the closed property with respect to this differential operator. We can reinterpret exactly the property of being a logarithm, of being a groupoid homomorphism. Therefore, S is a closed one cochain, and in particular, we can consider an exact cochain, which is expressed in terms of a function of omega infinity, and this is exactly this expression. So it's the difference of h of x0 plus x minus h of x. Okay, so let us now consider a specific example of this S, where h is basically the difference of hx plus x0 minus h of x, where h is just the Ising Hamiltonian for a sequence of 0 and 1. This map here, we pass from x to x minus 1 just to have a minus 1/2, 1/2, instead of having 0 and 1. Minus 1, 1. Okay, so on this space, on the space now omega infinity, we introduce a new measure using exactly this function h of x. B is still the Borel algebra generated by the cylinders, and now the cylindrical measure that we consider is generated by this function, this quantity here, which is 1 over zeta times the sum over all the x belonging to the cylinders of the function e to the hx. This zeta is just the partition function associated with this Hamiltonian. And what we are doing basically is to homogenize over the partition of the interval 0, 1 to get, when we consider this measure acting on a cylinder, we are homogenizing the partition function on a partition of the interval 0, 1. In a certain sense, we are introducing the an application of the renormalization group here. Now, what we can see is that we can consider on the groupoid G the product of the counting measure on the fibers on the group gamma times this new measure, depending on this function h. And what we can see is that this is still an arm measure, but now the radon-Nikodym derivative, so the modular function, is exactly e to s of h. So we have provided in this way a new groupoid algebra, nu of h. A of alpha of h, A of h is the left Hilbert, which is obtained as the bicommutant of the left Hilbert algebra of A of h. There is a canonical KMS weight with respect to the modular automorphism, which in this case corresponds to the multiplication by the function delta to the IT. Okay, so this is what I wanted to present. Thanks for the attention, and again, happy birthday, Ivan.
Thank you very much. Now there is some time for questions. Sachin.
Hi, Fabio, this is Sachin.
Hello?
Hi. So you mentioned that at some point you mentioned ergodic action.
Yes.
You have an ergodic measure. So I wanted to know if you've thought of computing dynamical entropies associated with ergodic action, and in particular, say the Kohn-Stormer entropy.
Well, I haven't done this, but of course, this is a good question. And it would be, I think that this actually was the Kohn's idea, whether all this construction is connected to a paper, as was told by Alberto previously, which Kohn introduced this non-commutative integration theory, exactly using groupoid. And so his idea was exactly to treat the case of singular action, and especially related to the ergodic theory, So of course there is a connection and can be done in this case, but I haven't done it yet. But so it's a nice question. Thank you.
I think this would be interesting because it is the quantum analog of the Kolmogorov-Sinai entropy. So it would have the quantum analogs of Lyapunov exponents directly, rather than trying to construct Lyapunov exponents that people try to do in this indirect way using OTOC and so on. So I was just wondering if you had thought about that. Thank you.
Thank you very much.
Hello, this is Govindraj, TRG. Just wanted to know, can dissipative systems be included in this kind of descriptions?
Well, I don't know yet, because up to now, what we are obtaining here are basically Tomita-Takesaki theory. So when we pass from a canonical KMS way to another one, they are usually connected by unitary operators.
Yeah.
So at this point, we are not, I don't know yet if it is possible. In principle, what could change, instead of considering this groupoid homomorphism, one should change for sure this property with respect to the inversion property. There was a paper actually by Schwinger in which he wasn't considering this property for his Lagrangian operators, and he was obtaining in this way dissipative system actually. So probably this is the way is to change this S from and we should not consider S which are groupoid homomorphism, but maybe only a category homomorphism, considering a subcategory of this groupoid.
Thank you.
I want to greet you, and I'm very happy that
Sorry, hello?
you greet
I
you.
cannot.
Thanks for coming and giving a very- That's it. So I do want to ask, modular automorphism is not necessarily the thing that governs time evolution in the quantum field theory context. There are other automorphisms, and the Hamiltonian, for example, is not necessarily given by the modular automorphism, like we know. Right? So, have you considered all the outer automorphisms of this algebra you are getting? And secondly, what is its connection to the Araki-Woods conception?
Well, I haven't considered all of the outer automorphism, but this is exactly the Araki-Woods construction. So in this case, we have considered only the groupoid of sequence of 0, 1, but actually one could consider sequences of 0, 1, 2, 3, modulo, some modulo n, and obtaining homomorphism between these type 3 lambda factors and them and these other factors that would be constructed in the same way. About the Araki-Woods construction, this is the connection that there is an isomorphism between the interval 0, 1 here and an interval of when we consider the sequences with more than 0 and 1 only. About the modular automorphism, here what we obtain, of course, one could consider as the classification of all the KMS states actually is based on this outer automorphism of the group of the algebra, but I haven't thought yet about how to implement them in this setting, to be honest. But of course, it will be next step in this case. The only comment that I can do here is that these Hamiltonians here, they are all unbounded from below and from above. So what is the connection here is more related to the notion of thermodynamical time that was proposed by Conz and Rovelli. So it's like having a reference time, and actually, it's more like in this sense that we are considering a reference time for this system, but in principle, there is not a time operator because it's not bounded from below. The Hamiltonian is not bounded from below in this sense.
Yes, that's what I was about to ask. This cannot be the Hamiltonian because system is unstable
Yes.
to delta. Yeah. Okay.
So it's like a reference system in this sense, exactly. And this is why one could consider again this addition of an Hamiltonian with respect to the reference one. In this sense, this addition of h of x is like a perturbation of the reference. In this case, what I've considered is that the starting groupoid algebra was the one in which delta was only 1. So was the case lambda equal to 1/2, which was the invariant measure. And what we have done in this case with this choice of this h of x is to perturb basically that the modular Hamiltonian with this term h of x. And this should, when we consider a different s of h, we are perturbing the modular Hamiltonian with these additional terms coming from this general solution S.
Just maybe it is useful for you. There is a paper by a Hungarian group, okay, which is very interesting for a lattice system, infinite lattice system, which admits a time automorphism with a Hamiltonian which is bounded below, and which also has order disorder parameters, and furthermore it is a half algebraic structure. And in fact, they reproduce all the Doppler-Haag results in their context, okay, including the Doppler-Roberts theorem on the generalization of the Tanaka-Klein duality. They reproduce everything. Okay. Maybe this can be useful for you to have a look.
Yes, yes, thank you very much. If you could send me the reference, it would be really useful. Thank you.
So, thank you very much for the nice talk. Let's thank the
Thank you.
speaker once again.
Okay, that concludes the session here. We have coffee at the Central Lecture Theatre at 5:30. It's in the physics building. And after that, there'll be the public lecture by Raphael Sorkin at 6 o'clock in the same place. So it's not here, we have to move elsewhere.